So first today I just want to, this lecture I'll just start with the R part first. So in this directory I have shared, it's called the class directory for today's class. There's this code, R code, that I've loaded on RStudio, and I have those two data sets, heights and phobes. Phobes I'll come to a little later in the lecture. Heights is what we did the previous lecture. So let's go back up. So once I come here, this I think you've already done in your previous lecture of installing tidyverse. So I need a ggplot, so I'll run ggplot. Now here, if you notice, I'm going to read the table from the file called heights.txt. So you notice that the heights is the same folder as the R code folder. So what I'll do first is I will go to session here and I'll set the working directory as the same place as the R code file, which is where the R code and the heights data is. So now you see it sets it correctly. It set the working directory to this, and then you can also check it if you want by running the command get working directory. It'll give you the exact where the directory is, where R is going to work with. So once I have that, then the first thing I can do is I can read the file. So let's see height data set. So I read it. So now if I go here or even here and I type in height underscore data and I run it, I can check it'll give you all the data sets that is there, right? This is, of course, it's dropping out the last 800 rows or so, but it's giving you the entire data set so far. So then the first plot that I did was I just plotted height, mother's height and daughter's height, and I did a geom jitter by 0.5, so as to sort of make sure we can see all the points. This is exactly what we did in the plot that I showed you in the previous class, right? It's all, and then of course the plot in the previous class was kind of let me go back here. So it's kind of all jittered like this, and because of the was compacted like this because of the PDF file. But this is how it looks like in the RStudio, right? Very good. So then I did this thing. I said, okay, fine. I did this three things, right? I did between 58 and 57, and 57, 58, 64, and so on and so forth. And I did this. I subset data set by identifying the rows like this. So I ran it like this, and I identified rows, and then I picked the rows, and I plotted this exact thing that I did. Three separate things I did, and I showed you that, okay, fine, hey, in this picture that I showed you that there weren't unusually tall daughters, no short daughters in the higher regime, and so on and so forth, and then no tall daughters in the mom side was small, but in the middle there was variation across the two things. Okay, very good. So now let's go on to the first exercise in linear models. So now here what I want to do is I want to use a. So here what I want to do now is that today is that in this lecture is to develop a technique, a methodology, more than technique. I want to. It's called. Let's say I'll just call it a particular method. Of course, it's not statistical. It's just what you would ideally do. Method, and what I want to do is I want to choose a linear model to find the best fit linear model. Okay, so this is like a brute force technique we'll do today, and then we do statistical analysis on this as the course goes along. Okay, so then the idea is the same thing. So I have y equal to, so this is the model, right? So y is equal to alpha naught plus alpha 1x, and then I want to find, given the data, I want to find alpha naught hat and alpha 1 hat that is the best fit for the data. So how to find is something that we will discuss. And then, of course, in the course, as I go along in the course, we will discuss many things. So we'll discuss, in the course as I go along, we'll discuss how good alpha naught hat is and alpha 1 hat is. We'll also discuss, is the linear relationship correct? Of course, you'll plot and check, but even after plotting, That is there actually a significant slope? So we can test, actually, we can actually do a hypothesis test, or I'll just call it a statistical test. Test is indeed alpha 1 0 versus alpha 1 not equal to 0. Right. We can test these things and so on. And then the other thing is that, of course, we can also do model validation. So this, I think, will be a little different from what you've done so far in machine learning and AI. Is that see there you'd have a training data set from which you would get the parameters. Then you'd have a query data set, which is about 80% of the data you would use for this, and 20% is this, and then you test it on the rest, and then maybe 60%, maybe not 80%, 60%, and then 20% on the side. But here I will not do it this way. I will try to devise statistical tests to do this. So we will discuss examples data sets as I go along in the course as well, and you should also think of it as these are not replicable data. There's not lots of data available. It may be a clinical trial. You can't repeat again, or you have a fertilizer and a crop yield. You can't just do it again. So it's like a real life experiments, and there's one realization of the data set. So the first thing I will do is I will just do a simulate experiment. So this is a simulate data set. So this is like we'll do it in R in a second. So this is called this is in a package called Model R. Model R package, and the data set is called Sim1. Sim1 is the data set. So it's a simulated data set. So it's simulated. It's not real. It's a simulated. Think of it as having two variables, y and x. Y is independent and x is dependent. And let's see. So and we'd like to know what can I fit a linear model to this. So first thing is that y is independent, right? Y is dependent, y is dependent, and x is independent. Dependent, and x is independent. And the model I'd like to fit is, I'd like to understand is that we see a linear pattern. We see a linear pattern. So let's say we observe a linear pattern. That's one thing we do. And the next thing we'd like to do is we'd like to find, let's say, A0 and A1 such that y is equal to A0 plus A1 times x. Right. This is one thing we'd like to do. Okay. So let me just go to the R studio first and show you the thing. So I run tidyverse, right, as before, and I load this library called Model R. If the package you have not installed, please install it. This options is just a small option that I want to keep in mind. And then the first thing I do is I plot this simulated one. So here you can see that this is the data set, this simulated data set of so many points. Okay. So then what I'm going to do is I want to find the best A1 and A2, right? So what I do here is, if you look at this, I just take, so I call it A1 and A2 instead of A0, A1. Let me go back and say A1 and A2. So let me call this as y equal to A1 plus A2x. So let me call this as A1 and A2. A2x. So here all I'm doing is I'm just going to simulate 250 slope variables and 250 intercept variables, and I'm just going to just brute force create a data frame called of A1, A2, and then all I did was I'm just going to take the simulated data set. I'm just going to plot all the lines. Okay, so let's see. So I've just plotted all the 250 lines that I've gotten, right? So that's what I've done. So let me go back to the slide and make it precise, make it so. So what I did was I generated A1 250 samples, A2, also 250 samples. So A1, what I do, I just set uniform. If I look at this, I took uniform between -20 and 40. That's what A1 I did. So let me write this down. So A1 is uniform -20 to 40. So I took 250 numbers between -20 to 40. That's A1. And this I took uniform. The slopes I took is between 5 and -5. So -5. Right. So there are 250 models on this plot, right? So there are 250 models on this plot. So first thing is there are 250 models on this plot. And many of them look really bad, right? For example, all these lines here look really bad, and then it's not like a thing. So, and then the key thing is we need to find a good model from this, right? So we need to find a good model. So we need to find good model, right? So how to do it? So one way to do it is that you have to find A1 and A2. So let's say that I'll just write down in loosely, I'll try and define this in a second, that are kind of closest to the data. That is the one that best signify the relationship between y and x. So what I do next is I do a little trick. So let me go here. So what I will do is I will just, I just chose one line. I just chose a line. Then in this line, what I do is I have just computed the residuals. That is how far the data is from this line. Okay, the simple thing. So what I've done is I've chosen, I think, the third line. I've chosen a line that is A1 and A2, right? I've plotted the line. And then what I've done here is that I've computed what's called the residuals. So what are the residuals? They represent the distance of the points from the line, right? So they are the distance of the points from the line. Okay, that's what the red bars are. So the red bars, right? So then now once I have this, I can now try to see. So like now I can do now can we set a criteria? Can we set a criteria to find the best model, to find the best line based on the residuals? Right. So one already I've hinted to you is that I've drawn these distances, right? So there's several criteria one can use. So one criteria one can immediately use is the following. So let me write this down. Let me write 3 criteria down. So the first criteria one could use is that you could just say that I could just sum the distances, right? So I could just sum the distances. But then here, let's see what's the good part about it and bad part about it. The good part, okay, it's an easy thing to do. You have the distances clearly, sum it up. But at the same time, what will happen is there'll be lots of cancellations. So if you have, let's say, in this case, this line might give you there's lots of cancellations. So you should be careful. So this is error in cancellation. That is, you'll have negative distances and positive distances, and they may all add up to give you 0, and you might think that's the best thing. That's not going to happen. Right? So then, what one could do is you could say, fine, I want to do this. I'll just go ahead and do sum of absolute distance. That is, I'll take every distance. I'll ignore the sign, and I'll just sum the actual mean deviation. So then what I would do is I would do it for every line, and then I would try to find the best line, right? And this turns out to be a little hard problem. This is not that easy to do. This is a hard problem. What turns out to be the easy one is the one that I'll do next, is sum of the square distances, and that's called the least square line. So this is called the least square line, and this turns out to be that turns out to be the thing that you'll always try and do. So, okay, let's go to the R part and let's try and do it again. So I picked the right model. So then I picked one line that in my PDF file I picked the third line, but I picked one line. The number is the 106th line, and it will plot the residue and then all the residues. So this line was really way below here. Here all distances are positive, so I'll get a positive distance in this thing. Right? So then I want to do this measurement idea, right? So let's go back to we'll come back to this line 49 in a second. Let's go to the PDF file. So here what I do is, let me discuss what all I'm going to do now. Okay. So here I have my data set. My data set is what? My data set is xi, yi, right? So xi and yi, 1 less than equal to I, less than equal to n. So this is the data set that I have, right? Very good. And then what do I do first? So first is I have this line right here, right? I have the line right here. So this is a1 plus x times a2, right? That's all this thing doing. This is just a1. Let me write this down. This is a1 plus a2 times x. That's what this is computing, right? This is what this is computing right here. Right. And then here what I'm doing is I'm measuring the distance from the data point to the line. So this is what the residual is doing. I'm just doing, right? And here I'm doing the residual square and taking the average, right? So I'm just doing I just call the root mean squared residuals. So what am I doing here in this step? So I have n data points. So I take yi and I'm subtracting it from the model. Model is a1 plus a2 times xi. That's what the model is giving me. Then I'm taking the mean of the square. So I'm taking the square first, right? And then I'm taking the sum of I equal to 1 to n. I'm dividing by n. That's the mean. And then I'm taking the square root, right? That's what I'm doing. That's what this step is doing, right? This particular step is doing this thing. And then what am I doing here in this thing? I'm using the optim function. So using the optim function in R. So optim function is a function in R that's very useful. It is used to find the minima. So find minima or the best possible, right? So then it just finds the best one, right? So it minimizes this over all possible a1, a2 I have. So it runs it over all the 250 lines that I have and finds the best one. Cool. Right? That's what this is doing, right? And then it also tells you what's the minimum square distance. So what is the least square distance achieved by the optimal line? So the least square distance achieved by the optimal line. That's what this is doing, right? So let's go back to the R code. Let's go here. So let's do this. Let's run this again. So here I just define this function. So again, this function code I have not discussed in class, but I think this is the simple one. So the function takes two values, inputs as mod and data, right? That's what it takes, and then it computes. Once it takes that, it computes the exact the difference of the model from the data set, and then gets the answer. Right? And the model function I've defined at the top, it takes the vector a and the data set and gives the answer. So data set has two variables x and y. It only takes the x variable in this fashion. Right? Very cool. Let's come here. So this, and then this is the model number, distance, and then I do the distance, this thing, and then I get the best optimum one, and then I do the best part, and I get the answer here. Exactly what I have. Very nice. Very cool. So now I've plotted the best line. So I've gone back here. I've taken the line as A naught is 4.44. So A1 is 4.22 and A2 is this one, right? So here I'm plotting the line y is equal to 4. Let me go back to the previous line, 4.22 plus 2 point something 05 times x. That's the line I'm plotting. That's the best line. And for that, I'm plotting the residues and the points, right? So I plotted the residues. The yellow is the residues. So these are the residues, right? Residuals. And it seems like a good fit, right? I mean, it's not. It doesn't pass through all the points. Seems like a good fit. Right. Quite nice. And of course, it's the best with regard to the least square criteria. But is it the best line? I do not know. That's something we should think about. Okay, let's go back and check. Let's go back and do the same thing. So I run this. I put various colors here. Run the geom plot again. This is exactly what I have. This is what I had in the previous line. Now one can also. I have done the same thing. So using this is using this LM function in R. So you come. So this is something that I did by hand, right? This whole thing I did by hand. So we can also use what's called the LM function in R. So you can use the LM function in R to do exactly what we did. So the LM function in R does everything that we did. That is, it computes the mean square difference and then gets the actual line. So of course it will do many more things. We'll come to that as I go along in the class. So I take again a similar data. I take the coefficient of the LM, which is exactly what I have, 4.22 and at the bottom 2.05, and then I can plot the same thing. It's the same line that I get here. So now let me just go to this last part. This is like a Forbes data set. So let me write this down. This we'll do next exercise. This also I've given it in the R class. So it's called the Forbes data set. And so this measures atmospheric pressure and boiling point of water. So this is on the x-axis is boiling point of water, boiling temperature of water. On the y-axis is atmospheric pressure. So I've done this in one shot. So I think it has 17 data points. So let's write this down. Let's just check it all. Let's check all this in a second. So let's write this down. So it's 17 data points. And I just use the LM line to plot the best function. So I use the LM function. So I use the LM function now to find the best line. So the best plot, the best model, the best line, use the LM function, inbuilt LM function. That's what I did. Right? Okay, let's see. So let's go to this thing again. Again, if you look at this thing, I have stored the Forbes data set in the same directory. So the working directory is still the same. So I can go read this file. And then here I just plot the data set. Let's see if it comes. And then let me just go to A, and then let's try and plot A. I called it A by mistake. Let me just plot A, and then let me see if I can plot A. So this I use the geom smooth thing, and the method is the LM is the linear model method I wanted. So it gives you a straight line without this. Right? Of course, you could just do without it and then check the same thing as well. So let's see, maybe we can do that. Let's do this. Let me copy it and then. come down here after A, just to do this, and then let me just plot it. Let me run this thing. So if you run this is the plot, and then you can clearly see there's a straight line, right? This straight line. Then you can use then I use this A where I did this geom line as well, and then that gives you the answer. So let me just move it up. So this is A, and then I'll remove the A as well. So do A. This gives you the line. So then I can also do this, like I said, I can do this, I wanted both the Forbes residual as well. So I do the Forbes LM. So I do the linear model function, that's the LM function. Then I compute the residuals using the RISID, this command. It gives the residuals from this LM function. It's inbuilt already. And then I can plot this, I guess forget this B, and then, let me do B, it's not a problem. So I do B, and then let me go here, let me run the B, and then, so here I have this, I have plotted all the residuals. So the residuals of all the points are at this, so they're quite small. There's minus 0.25 to plus 0.25, and there's one little bit high at 0.5, it's quite small. Then I have this, I use the GG arrange package, so we have two things. And then it's not available. Let's see, could not find. So let's see. So maybe it'll not come in this. Let's just let's see. And here I did. Okay, let me come back to this in a second. So here I plotted the residuals and the graph on the same axis. So here if you look at this, the whole thing is that the linear model gives you a linear line, and the residuals of this kind. In this sense. So it's not a bad. So this is like maybe marked in orange. So this is like the largest residual, and somewhere here is the most negative one. Right, this is the most negative one, the smallest negative. That's how the thing looks like. And this I'm just plotting the residual, that is the pressure to the point on the line. Right? That's what I'm doing, right? So there's one interesting thing is that if you look at the physics literature, the physics theory is the following. The physics theory is that that log of the pressure is linearly related to the temperature. So that's the model in physics that they think the system should obey. So here I plotted the log of pressure versus temperature, and the line is and the residuals are much smaller. So of course there's one large one. There's still this one outlier. But otherwise, everybody is quite close by. Everybody has small residues. So this is like quite a good model. So this also one must sort of see at what scales the two variables are related. So one is you can think of pressure and temperature and see if it has large residues of all kinds. But if you do log pressure versus temperature, the error comes very, very small.